Hi folks, DavKiss here, and welcome back to another episode of DavKiss Builds. On the last episode, we determined what our input value range is by turning on the transmitter and receiver and seeing what we got on the Arduino over the serial connection to my computer. So now that we know what that range is, it's time to condition that range and process it so that we can turn it into an output signal that the LEDs can use to turn on and off. But before we get to that, there's a couple of topics that I need to talk about first. The first topic is constraining. So we have a signal that is roughly 1,000 to roughly 2,000. What we need to do now is take any values that are outside of that range and constrain them into that 1,000 to 2,000 range. The next thing we need to do after constraining the range is mapping those values. So once we have our values ranging from 1,000 to 2,000 from the input from the receiver, we need to map those values to a completely different range so that we can output values to the LEDs. So to do that, we're going to use mapping, which takes a value and its relative position in the first range, so our input range, and maps that to a corresponding value in the same relative position in a different range, or our output range. So our input range is 1,000 to 2,000. We need to map the values within that range to a range that is 0 to 255 for the output. Now here's a reminder of what our channel mapping looks like on the transmitter. We need to pay special attention to the 3 channels that are going to be one-dimensional. They're only going to move in one direction, and we're going to map those a little differently than we are the other controls that start in the middle rather than starting at one extreme. Okay, now that we've covered all of that, let's take a look at the code we're going to use.
This is the program I will be using for the final version of the proof of concept build. What this program does is it takes the input value from the receiver and converts it to a value that we can use to drive the LEDs. To start, I have this array up here, which has the pin assignments for each channel, very similar to the program from the last video. And then here I have all of my LED pin assignments, so the red, green, and blue for one LED, and then the red, green, and blue for the other. Now here is the receiver range, and we found in the last episode that it goes from 1,000 to 2,000, and I also have a middle range here, which will become apparent mostly for the two-dimensional controls. And I wanted a way to where if for some reason this range changed, if I used a different receiver and that receiver gave me a bit of a different range, I could change it easily here without having to change it multiple places down below. Similarly, I also have the pulse width modulation range from 0 to 255, which will be used to drive the LEDs. Now I have 2 arrays here that are just initialized to 0. This is the input signal, so this is going to house the value that comes from the receiver. This array is going to be the output array, so this will be the converted value that will be used to go out to the LEDs. I mentioned in a previous video that I was going to set something up to where I would be able to tell when the transmitter is on or not. And so this is where this variable comes in here, this TX online. When this is false, this means that the transmitter was found to be offline. And then when we do detect that it's come back online again, we can set this to true. And we'll see how this gets used in a bit. For our setup method, we start up our serial connection, and then we set up all of our receiver pin modes to be inputs and all of our LED pins to be outputs. Now for our loop method, there's going to be quite a bit going on here. But what I'm going to do is I'm going to talk about the method here, and then I will come back to what that method actually does in a bit. But each of these methods is actually named so that you can tell what it's doing without actually having to see what it's doing. So we're going to loop from 0 to 5, just like we did in the last video. This will get us channels 1 through 6 from the receiver. So we're going to read in the value from the receiver. If the input value is not 0, then we're going to set the transmitter as true, meaning that the transmitter is online. If it is 0, then we're going to skip all of this and come down here and set it to false so that we can show that it's offline. But when the transmitter is online, we'll set this value to true, and then we're going to write out whatever the input value was that we got from the receiver out to the serial connection so that we can view it in the serial monitor. Then we're going to do some conditioning on that signal, and this is where the constraining comes into play that I talked about at the beginning of the video. Now, once we have our signal conditioned to be in the specific input range that we want, we're going to do a couple of things here. So this switch statement basically says, depending on what this value is, do something very specific. So for channels 2, 4, and 5, or rather channels 3, 5, and 6, this is going to be the throttle and the 2 knobs. These are what I consider one-dimensional controls, meaning that they start from one extreme and go all the way to the other extreme rather than starting in the middle. So we're going to do some different mapping for those signals, and then all of the other channels we're going to use as two-dimensional controls, and we're going to map those a bit differently. So for each of these values of I, which are going to map to the channels, we're going to map these to the one-dimensional, and then any others we're going to just default and map to the two-dimensional. Now, once we have our mapped pulse width modulation values, we're going to write that value out to the serial connection. And then, as I said earlier, if we get a 0 for that input value, we're just going to set that transmitter online to false. Now down here, if the transmitter is online, then we're going to write the pulse width modulated values out to the LEDs. Otherwise, we're going to print a message out to the serial connection saying no transmitter signal, and then we're going to reset all of the LEDs. This way, while the transmitter is offline, we're not printing erroneous values out to the LEDs. We just turn them off. And then to keep the serial output clean, we'll do a print line so that after all 6 channels have been read, we jump to the next line on the serial. So that's our loop function. We're doing quite a bit in there. Now let's talk about some of these individual functions in here that I have methods for. The read channel function does exactly what you would think it does. It sets the input array value for the specific position for that channel to the value of the pulse position value, so how much time is in between a high pulse on the specific input channel. The serial signal write just takes whatever that value was, and for the specific channel value, so we do again the channel value plus 1 since the array is actually 0 based, and then we just write out the input value that we found from read channel. The serial PWM write does the same thing as the signal write except for the pulse width modulated value that we found. The condition signal method is where this constraining is going to come into play that I talked about at the beginning of the video. So what we're going to do is we're going to give it the value that we found from the receiver and then give it the low and the high value for the range we want to constrain it to. Now, if this value falls below the receiver low value that we give it, then the constrained value is going to just be set to whatever that low value is. And the same thing for the high value. If this exceeds the high value, then it's going to return just that high value instead. So we know that when this is done, this input value will be between the receiver low and receiver high values that we set earlier. So in this case, 1000 to 2000. Now the other thing I'm doing in here is largely for the two-dimensional controls. The one-dimensional controls will not really see much effect from this, but this will help kind of center our two-dimensional controls a bit. So you may notice that I had that RX mid value that was set to 1500, the midpoint in between 1000 and 2000. So what this does is it does an absolute value of the midpoint minus whatever the input value was. So basically, if this input value is within 20 on either side of the midpoint value, so that's 1520 to 1480. So if it's within that range, we're just going to set it to that midpoint value. And this is going to have sort of the effect of when you let go of if you're close enough to the middle, we don't want it necessarily bouncing around. We want it to stay at a very solid value. So we're just going to set it to that midpoint value so that if we're not touching that control, then it will stay at that value. All right, so now we're going to get into the signal mapping and the difference between the one-dimensional and two-dimensional controls. So first off, we're going to set this temporary value equal to the input value that we got from the receiver. This isn't really necessary for the one-dimensional. It is for the two-dimensional, but I wanted to kind of have these sort of match the same format. So we set this temporary value to the input value. Then we're going to use the map function. And what this is going to do is take our input value and we're going to provide it the low and high values of the range that this value is within. So this is going to be that 1000 to 2000. And then the range that we want it to map to. So this is the pulse width modulation range of 0 to 255. And so what this is going to do is take this value and put it in the relatively same place within the range that it is in here in this range. So if this was a 1500 exactly between 1000 and 2000, this would map to a 127 in this range. So that's all this does is it takes this value and places it in this range based on its relative location in this range. For the two-dimensional signals, we're going to do something very similar, but with a couple of changes. So we're going to set our temporary value actually equal to the absolute value between the midpoint of our receiver range minus the input value. And what this is going to accomplish is centering 0 for the middle of our control. So since the default position of these two-dimensional controls, so for on the right stick, it always defaults back to 0 when you let it go, we want that midpoint to be 0 in our pulse width modulated range. So to do that, we take that absolute value and then we're going to map that value to the pulse width modulation by starting from 0 and then going from the number of values within the full receiver range, so in this case it's going to be 1000, divided by 2. So this is actually going to have a range of 0 to 500, or the midpoint out to the extreme. So we're going to set 0 to 0, or 500 equal to 255 in this case. And then the last two functions are fairly straightforward. We're going to write out our LED values to each of the pins for the LEDs. And then the last one is just going to reset them to 0. So these are going to use the analog write. This uses the pulse width modulation to write out the value that we found in the mappings out to those individual pins or set them to 0. All right, so I have the new code uploaded to the Arduino and I have powered it on, and so you can now see the no transmitter signal logging to the serial connection because the transmitter is currently off. So I'm going to turn the transmitter on. All right, and now we can see we're starting to get data, but because of the way that we set up all of the mapping, all of the default positions are now at 0. And this is indicated in the serial by the number in parentheses next to each channel. So the first number in each channel is going to be the input value, And the second number, the one in parentheses, is the output value, the pulse width modulated value. So now let's try it and see if it works. So on the right hand, on this one, we're going to do the up, which should be red. And we see that as we push it forward, it gets brighter. And we can see that now on channel 2, we've got just about to 255. We could probably do a little more with this, and I can come back to that a little bit in the next video. But we're going to actually bring that back down, and we see if we pull it down, it also goes to 255. So we bring that back to the center, it goes back to 0. And then the same thing with left and right. This is going to be the green. And so if I put it about halfway, we see it's about half as bright. And if we go over there, and what's real fun about this is, and I don't know how well this is going to show on camera, but let's do just a little bit there. And then, yeah, that doesn't show up very well just because of the green is so overpowering compared to the red. But so yeah, we get the red, and we get the green. Now on this side, on the left LED, if we push this up, we get red. Push to the side, we get green, which is cool. And if we bring it down, we see that the brightness kind of comes down a little bit. So that right there is actually sort of a yellow, but again, the green is overpowering, so you can't really tell. So that's the way that looks. And then of course, you know, this control is one of those one-dimensional controls. So we've got the entire span here, whereas here in the middle is going to be 0, and it gets a lot brighter, a lot faster because of the fact that we're using half of the input range. And then of course we've got these knobs at the top here that control the blue. So if we do blue and red, hey, we get kind of a purple color now. So you can actually mix the colors. And this is actually going to be really important, this concept of mixing these signals together. This is going to be really important when we start talking about actually driving the car once we get it all set up, because of the fact that we'll have to set this up to where when we want to turn, we're going to have to take a mixture of either this throttle and the left and right here, or maybe the left and right on this side. That's going to be part of the decision making on this, is how to handle turning on this, because of the fact that it's going to be a mixture of 2 different channels, the forward and back for the speed of the car, and then the left or right based on how much we want to turn, how fast we want to turn, and in which direction.
And there we have it. We have a successful proof of concept where we took an input value from the transmitter and translated it to an output value on the Arduino, and made something in the physical world actually happen as a result. So what this means is now we can take any of these signals from this transmitter and do whatever we want to with them. So the first thing that we're going to do is actually try and make motors run so that we can actually create our remote control car. Before we move on to the car though, there's one other thing that I want to do first, which is expand the transmitter to, instead of just using 6 channels, we can make use of all 10, which will include all of the switches on the top. So that's what we're going to do in the next episode. If you haven't seen any of the previous episodes of how I got to this point, I highly suggest you check out the playlist that has all of those episodes, and so you can see how we got from point A to point B. And if you want to see where all of this is going to end up, please hit that subscribe button so that you can see when I have a new video posted. With that, thank you so much for watching, and I'll see you next time.
I mentioned this variable. No, I didn't.